Okay. Good morning. So these two lectures, the point is to introduce an abstract machinery that will allow us, first of all, to have a common language for all these problems that we were discussing in the past weeks, like zero set or interpolation in infinity or peak interpolation. Even the silent sampling theorem will be somehow in this general context. And it will be, machinery coming heavily from functional analysis, in particular reproducing kernels in the spaces. This context will not solve all of our problems. It can do many things for us, but many more than one could expect, I think. But yeah, that's the point. So it's so the topic is producing a kernel and Hilbert spaces. So if we want to talk about the idea is that our functions belong to some Hilbert space states, so some vector space with a norm coming from a linear product with which it's complete. And the point is that if we want to talk about interpolation problems, we want at points, we want our functions to have meaning defined in the points. So in particular, it wouldn't make sense to consider spaces, I don't know, like L2 of R consisting of functions which are only almost everywhere defined, so it does not really have a meaning to talk about the value of the function at the point. So we will require our abstract Hilbert space to be a subset of I don't know, functions defined in some set X. So X is just one non-empty set. And our Hilbert space is a subset of functions on this set. And the crucial property is that it has meaning to define to say what these functions are at points. A more functional analysis way to say it is to say that these linear functions which take, so this function which depends on a point in the space and takes it takes a function and evaluates it at x is around linear function. And that's the only axiom that we require from our space. For precisely this reason, because our functions have meaning that define the points. Okay, and then immediately we can see that since these functionals are bounded linear functionals, we can represent them through this representation theory by some element in the space. So this is going to be the inner product of F against some k x depending on the point for all F in the Hilbert space. This is the inner product of the space, of course. And so these are kx are just vectors in A at other functions. And you can see immediately they have some symmetry properties coming from the properties of the Hermitian inner product. For example, if I take kx and evaluate it at x, this is that kx against kx, which is the norm of kx, where this is positive. So here I will assume that this I will call them kernel vectors are non-zero. So I will assume that kx is always the non-zero vector for every x. Because otherwise, you see, if for some x this vector is a zero vector, then all functions vanish at this point. So it's somehow a redundant point of the space, and I can remove it. So I will make this assumption, harmless assumption. Let me assume that this is always strictly positive. Or you can see, for example, that k at x evaluated by y is that kx against ky, and then the inner product is Hermitian. So this is conjugate ky inner product kx, which is the ky kx. But okay. So it is also conjugate symmetric and positive at the diagonal. Okay. So we need some examples, of course. We saw already one example, which is the Pauli-Wiener space. And I mean, Nicole, I think next week we'll talk much more in detail about the Pauli-Wiener space. I will give a very naive introduction, a very naive proof that this is a reproducible kind of hero space, but we can see that much more in the set. For example, remember that this Pauli-Wiener space alpha was functions in L2 of R, such that the Fourier transform, the support of the Fourier transform was between minus A over 2 and over 2. And the norm is a norm in the L2 norm that's seen as a subspace of L2. These are continuous functions since the Fourier transform is compact, and we can show that it is actually a reproducing kernel Hilbert space. So remember, I write it here. This is the Fourier transform as we used it at the time, as I will use it now. And remember that when we proved Salmon's sampling theorem, we had this function. What is it? We had this function is associated to some point x0 in R, which was given by A times the sink of dA x minus x naught. And the point was that the Fourier transform of this function was the characteristic function of minus A over 2 A over 2 times e to the minus the plus minus 2 I okay. And we will show in fact that this is the reproducing kernel at the point x0 for this space. That is because if you want to evaluate some function in the Pauli-Wiener space at some point at x0, you can write it as, you can use the inversion formula from Fourier theory, and you write it as the inverse Fourier transform of the Fourier transform at some point x0. Okay. The inverse, okay, let me calculate the inverse Fourier transform. Is just the Fourier transform at the negative at the point. And it's the inverse in the sense. is in this. And this is the integral from minus infinity to infinity, as we define the Fourier transform of the inverse Fourier transform of f at the point which I call x e to the minus 1 I x. Okay. But as I said, the Fourier transform is just the inverse Fourier transform is this thing here. Okay. And now we use the fact that this Fourier transform is supported only in minus 2a over minus 2a over 2 a over 2 in this interval. So it's the same if I just throw in a characteristic function. Okay, I said I first changed the values. I put minus x equals x minus and I throw in the characteristic function. But this is that exactly the conjugate of the Fourier transform of this. It says kx0 y Fourier transform conjugate. And by Planck-Schmelz's formula, Planck-Schmelz's identity, you can just remove the hats. Okay, and this is the inner product of f with a of x. Probably Nicola had already proved this, but this since this kx0 is a function in L2, this gives me in one shot both requirements. First, that point evaluations of bounded linear functions, like a Cauchy graphs, essentially, because this is the Cauchy graph less than the norm f times the norm k 0 in L2. And it gives me exactly the formula for the kernel also. This is the thing. Okay. As I said, what I did here is not complete in the sense that these functions are not only defined on R, but can be extended to entire functions on the whole complex plane. And this is what Nicola will prove in detail next week. The other very interesting example is the Hardy space, which lives in the unit disk. So the Hardy space in appearance is just another representation of little 2. It's just functions holomorphic in the disk with they have, of course, part here is representation, and the norm is defined as this L2, little norm of the coefficients. So clearly, this is okay. Clearly, yes. that we first proved that it is a reproducing energy space. Yes. Okay. Yeah. So I say holomorphic in the disk. Okay. Let me show that if you have this these are two convergent, then actually these are functions well defined and holomorphic in the unit disk. That is because you evaluate some finite sums and then by Cauchy matrix again, this is less or equal than the norm of what they call the norm of F, the equal to norm of the coefficients times this geometric series. So again, by putting some finite sums here and then taking a limit, this proves, first of all, that this defines a holomorphic function in the unit disk, where this partial function was uniformly an absolutely compact set by Weierstrass set. And then it also proves in one strike that point-wise evaluations are bounded linear functions. Again, because this is now I take the limit, it's a non exist. This is the actual value of f of z, and they prove that this is less than the norm of f in a Hardy space. Back to the bottom. Times some constant, which depends on the point, of course, right? I didn't make any claim of the uniformity of the norm of the points of these linear functions. It's just finite for its choice of them. So yeah, this proves that this point-wise evaluations have norm less one. So the Hardy space, is just another representation of Little 2 for every Little 2 sequence. You construct a holomorphic function which converges in the polynomial disk and vice versa, and it's a reproducing kernel Hilbert space. Like this, and we can actually calculate the reproducing kernel again of the space, which is as follows. So of course the norm comes from an inner product, which is the inner product of Little 2. So we know actually that there exists a function kz holomorph in the Hardy space, so holomorphic in the unit disk with the coefficients in Little 2. So it must be of such form. And coefficients C n, which depend on the point, times W n, where these are living Little, which has the property that if I pair it with a function, it gives me the value of the function. But I know what the pairing is if, let's say, I write FP power series. So the pairing is just the Little 2 pairing of the coefficients. So K, Z, F, sorry, F key. Is the sum of the coefficients of F times the coefficients of KZ bar. And what I claim is that this must be equal to the value of f at z, which is just a n to the n. I know that kz exists and it's unique, so I just have to choose Cn properly, and you can see that the right choice of Cn is just the bar to the end. If I choose my kz in this way, then every time I pair it with an f, I get back the value of the function f at z. So in the end, kz of w has a particularly simple expression. Is that z bar w to the n, which is the power series, it's a geometric series, and it can be. So we have also an explicit formula for the reproducing kernel of the Halley space.
Sorry, why Cn is the bar?
So here I can just guess in the sense that I know that it's Cnz exists, and I know that they are unique by the Riesz representation theorem. So the only thing I have to do is that to guess the right choice, and to guess the right choice here is quite straightforward, because if I want this to be equal, then I can just equate this to that.
Okay, thanks.
Okay. So we have two examples. There are, of course, there are much more examples. We will mention some of them, not that are particularly interesting. Yes. So I wanted to go into another feature. I will go back and forth between the abstract and the concrete, in the sense that introducing some ideas for abstract reproducing kernel Hilbert spaces and applying them to these examples to see how they work. So the next thing that one can define is the multiplier space. Okay, I don't know how motivated it will be right away to define the multiplier space, but I hope I will convince you in the next 20 minutes that it's a nice language to incorporate all this fit interpolation and comparison interpolation here. So again, we're in the abstract. We have reproducing kernel Hilbert space A with helpful kernel kz defined with some domain X. The multiplier space, denoted like this, is just functions phi such that if I multiply the space by these functions, I remain in the space. And this means that I multiply any, this means that for every f in x, p times f at the point-wise multiplication of functions belongs to this. Okay, for one thing, the name is quite well motivated. We multiply the spaces itself, we are multipliers. The point is that, in fact, they define so somehow a phi in the multiplier space. So it gives rise to an operator multiplication from x to x. So here I just rewrite things. I just say that taking a function f to p times f is a well-defined operator just by how I chose phi. And it is linear, of course, because if I take a product and it's yeah, because complex numbers. And it is, but it is also bounded in the sense of operators. So I claim that that these are bounded operators. So they have finite norm. So the definition is the norm of these operators, and they claim that this is finite. And this is by the closed graph theory, because these are closed operators from how they are defined. That is to say that if I take Fn, so I want to apply the closed graph theory. If I take Fn, which converges in F in X in norm, and if M phi of Fn converges to some G in norm, then this implies that Fn paired with any vector Kx converges to F Kx. Strong convergence implies weak convergence. In fact, and this is to say that Fn of X converges pointwise to F of X. So what I say here is that convergence to the space implies pointwise convergence everywhere. And by the same token, if Pfn converges to G, then P X of Fn X converges to G of X for every X. But I know that Fn converges to F, so this converges also to Phi times F. So G of X must be Phi of X times Fx. Or in other words, G must be the operator P of F. And by the closed graph theorem, this operator is bounded and it has a finite norm. Okay. So in particular, implicitly, I put a little more in there. I put some continuity properties. Yes, and these are so these are the so you have to think of multipliers in a dual way, in the sense that that they are functions, their multipliers are functions on the space, but it is also an operator algebra. So multipliers can be seen also as embedded in the space of bounded linear operators of X by this correspondence. And in fact, we make this correspondence isometric by just defining the multiplier norm of the multiplier to be equal to the norm of the multiplier operator in the space of bounded linear operators. Okay. So now this really becomes an isometric embedding of the multipliers into the space bounded linear operators of H. So one further step can be done by looking at the adjoint of a multiplier operator. And I think this is really a simple but very, very ingenious, let's say, idea. That if you look at the adjoint of the multiplication operator, it has a really nice operator theoretic property. So have this proposition. So if we take multiply, then we have this property. So if you apply the adjoint on any kernel vector, this is an eigenvector, and the eigenvalue is just the value of the multiplier of z conjugate. And this holds for every z. Which shows that the adjoint is a very particular structure. Okay, every kernel vector is an eigenvector, and it's an extremely useful property. You will see why in a second. Let me prove it first. Okay. We want to know something about the adjoint, so we have to pair it with something to use to define the property. Okay, so I take f in it. And just bring it on the other side and p. And now this is the 3 times f paired with the kernel vector, but by definition the kernel vector reproduces the value of this function at the point, so this is p of z times f and z. And okay, the trick is just to reuse the reproducing property just for f this time and treat this as a number. And now you can see that if I want to prove this, I better bring this on the second side with the conjugate inside. And this holds for all f. So the second part of the inner product have to coincide. This implies that exactly the thesis of the proposition that this is equal to. As I said, it's extremely elementary, but for example, it gives you the following immediately. That so since these are eigenvalues, they lie by definition in the spectrum of the operator. But this lies in a disk, closed disk, centered at 0, and radius the norm of the operator, which is the same for the adjoint and the operator itself. So what I proved here is that the modulus of phi cannot be bigger than the norm of the multiplier operator, which does not depend on z. Okay, so I proved that phi, if phi is a multiplier, it must be uniformly bounded. this is less than, and I write here just the way I define it, this is multiplier property. Okay. So you see, as a corollary, I get that multipliers are bounded functions always, uniformly bounded functions. And this is okay. So good. Let's go back to the concrete. We had two spaces in the beginning. The Hardy space and the Pali-linear space. At this point, I cannot prove to you which are the multipliers of the Pali-linear space. Nicola will, after Nicola's lecture, we will be able to see that the Pali-linear space has no multipliers. So this is not very encouraging because because we did all these beautiful things and then we have an empty space. But this, okay, this, okay. There are spaces which have very rich multipliers, thankfully. So this is not an empty theory. In particular, the Hardy space has a very rich multiplier structure, and we have already encountered the multiplier algebra of the Hardy space. I will prove now that this is exactly the space of bounded holomorphic functions in the unit. Yeah, so when you start a new theory, always check that you have some trivial examples. Otherwise, you can prove anything. So I want to prove the following, that the multipliers of the Hardy space is infinity. It's infinity with holomorphic functions bounded in the unit definition. We know already that multipliers must be bounded. We just proved it. And the constant function 1 belongs to the Hardy space. Right? So if I take a multiplier phi, and I multiply it by 1, I must be in the Hardy space, but this is phi, and phi in the Hardy space in particular is holomorphic. So I know that multipliers must be bounded holomorphic functions. Let me not put it in the detail. So in particular, I get this inclusion. Okay, because I know that multipliers have to be bounded. If the constant function 1 is in the Hardy space, multipliers must be holomorphic functions or holomorphic bounded functions. By definition, it's infinity. And this concludes this part. For the other part, I think I can say confidently that you can try as hard as you want by using the definition of the norm in terms of coefficients, and you will not be able to prove the other inclusion. But you have to use some kind of integral representation of the norm. But in this case, it's just Parseval's identity. So before I prove the other inclusion, I have to rewrite my norm in the space in a way. So just take F in the Hardy space. The norm was by definition the sum of the Taylor coefficients. And to do my trick, I need an epsilon of room, let's say. So I introduce this parameter. Here, just introduce the soup over R, which I think of as a rate, but anyhow, which of course retains for R equals 1. So I can put it for free. But now I can apply Parseval's formula. So let me rewrite it as Rn is n squared. So I think of this as coefficients of some function in the circle, as Fourier coefficients of some function in the circle. And Parseval's formula tells me that the L2 integral of the function in the circle is equal to the sum of the squares of the coefficients. But since these coefficients decay exponentially, I have convergence uniformly on the circle, so I can just literally write. Because this is again this is the value of my function f at R to the E I theta. So this is that's the soup. And this gives me the integral representation of the norm I needed to go further into this proposition. I don't know if you can see it, but now it's what I want to prove is that if I have a bounded holomorphic function, then it is a multiplier of the space. This means that if I have a phi remains infinity, I want to prove that this norm is finite for every f. But now I can use this formula, which makes estimate much easier. So this is just the soup. And the theta. And now I can pull out phi by majorizing it to sustain some, which I know it's bounded by some uniform quantity. Let's call it H infinity normal phi. And what remains inside is that exactly these two normal factors. So then proving that H infinity functions are multipliers is just one way. So Okay, we have the Hardy space for which multipliers are non-trivial. There are a lot of them. And this already might indicate to you why there is a connection between the theory of multipliers and the interpolation problems that we saw before, like Fick's interpolation problem and Harleson's interpolation and so on. So before I do a small break, just notice here that from this inequality, we not only get that phi is a multiplier, but we get that the multiplier norm of phi is less or equal than the AC infinity norm of phi, so the subnorm of phi. But from the abstract result, we know also that the multiplier norm of phi is greater or equal than the subnorm of phi. So in particular, the multiplier norm of phi in this case is exactly equal to the H infinity norm of phi. Okay. So the identification here is done in a geometric with the norm coming from the multiplier norm and the H infinity norm. And that's okay. Let's have a break and then we continue with the abstract peak problem instead. And now we arrive at the fun part because we can formulate an abstract peak problem. So remember, peak problems, was the following. I am given Z1, Zn in the disk, and W1, Wn in the disk. And I wanted to answer to the question if there exists a function P, which is bounded of norm 1, for this I mean the unit ball in H infinity, such that f of z I is equal to Wi, for I is equals 1, 2, n. And then Fick's theorem was that this is possible if and only if this matrix was positive semi-definite. So here I mean positive semi-definite. And the only to formulate.
Nico, sorry, what is H1 infinity?
Yeah, so it's the unit ball in H infinity, so it's just functions holomorphic in the disk, such that the soup is less or equal than 1.
Thanks.
And so to formulate an abstract peak problem, the only thing we have to do is to remember from before that H infinity was the multiplier algebra of H2. So we can ask if I'm given, so this is the abstract peak problem, if I'm given H reproducing kernel Hilbert space, and I have some points in my domain where my functions are defined, and some values that I want to interpolate. Let's put C. Then I want to answer the question: does there exist a function P, which is the multiplier of the space norm 1. So here again, I mean the same thing. It's a multiplier, that's the multiplier norm of P. It's less or equal than 1. Such that P of Zi is equal to Wi. And that problem, first of all, it makes sense. Secondly, it coincides with the classical peak problem if H is the Hardy space H2, because in this case the multiplier algebra is isometrically isomorphic to H infinity, so the unit ball of the multiplier algebra is exactly the unit ball of H infinity. Yes, and since okay, here I put C, but in fact, since I require the multiplier norm of P to be less than 1, this means that also the Shoup norm of P is less than 1, because remember we proved that the Shoup of P is bounded by the multiplier norm of P, so it's the same. I put here the B's. Okay, I want to be really precise, close this, because I can have things of modulus 1. And so what happens here is a very good example of the theory, I think, of reproducing kernel Hilbert spaces, because one direction of the theorem, it really holds for every possible reproducing kernel Hilbert space, the necessity of the condition. The other direction, the sufficiency, is really a property of the specific space you choose. So what we see is that we can formulate the positivity condition which is necessary for every conceivable reproducible kernel space, but it's only sufficient for some of them. So this general theory that we are building, it cannot solve any problem for us, but it can do something for us. So what I want to prove.
What do you assume equal to 1?
Yeah.
No, not
yeah. If you can have a multiplier of norm exactly equal to 1, but for example, if it can happen, even so, this is a.
I was thinking of unities.
So it can happen that if you have 1 point, you can. I mean, you have constant functions which you can interpolate 1 point at the.
Okay.
So you can have the some constant function. You could have. So in the yes, you have now this constant function 1, which is in the closed unit ball of the.
That's the only case for the hard.
For the hard state, that's the only case, but in general, you could have multipliers of norm 1 which are not constant, but it's really. Okay. So. So the necessary condition is the following. So we want to prove this proposition. It says if star has a solution, then the matrix 1 minus Wi Wj bar, and here becomes the kernel playing a role. This matrix is positive, semi-inversion. As a finite matrix where Ij from function. So you see that this is in this abstract setting. This part 1 over 1 minus J bar becomes the kernel of the particular Hilbert space we chose. Okay. And of course, in the case of the Harvey space, this kernel we computed before, it was that 1 over 1 minus J bar. So it's exactly the same condition formulated for a general reproducing kernel Hilbert space, and it's always nested. So solution of the interpolation problem implies positivity of this matrix. And this is where this theory comes very handy, because it tells you that in fact this is some abstract Hilbert space property, it's not really some hard fact about holomorphic functions. And this is clear, I think, from the proof. Okay. Just translating things. What it means to have a multiplier of norm less than 1? It means that the multiplication operator has norm less than 1. And here again, there is this nice idea that things are better for the adjoint. Calculations are easier for the adjoint. So this is the same to say that the adjoint has norm less than 1. Of course, they have the same norm. Which means, again, that by rewriting, that the norm of the adjoint applied to some f is less or equal than the norm for every f image space. And the last conceptual idea of the proof is that you would like to apply this inequality not to any f, but to just f that belong to a finite dimensional subspace, which is spanned by the kernel vectors. So I just want to check this condition. So this implies in particular that the squares for the calculations to follow, but this implies in particular that this holds for all f in the span of the kernel vectors k, z1, k. Of course, holds for all f. And the conceptual idea that the proof finishes now here. I mean, now you just have to compute things. So what is an element in this span is just a finite linear combination of the kernel vector. By the way, carefully here I chose the kernel vectors are chosen, and the kernel vectors associated to the points that I want to interpolate. Okay, it's not some random Kepler vectors. So F is of this form, where Ti are complex numbers. And I go and I compute the right-hand side. I will erase that, but remember that what we want is the interpolation in the sheet. Somewhere there. So the right-hand side is the norm of Pi K Z I. I use the inner product that I have. Not I use the linearity of the inner product. This pi. Pi is with bar, and then I get the inner product of the pi. But by the reproducing property, I with bar K. So that was the right hand side. What is the left hand side? The left hand side is I write it like this. Okay, so I write as the inner product of M star P F with itself, and then I bring M star P on the left and becomes empty. And then I just substitute again the expression for F. And here again, it's very here I use the fact that first of all, it is the linear operator, I can bring it inside, and I know how the adjoint acts on kernel vectors. They are eigenvectors. So, okay, I can bring the sums outside. So we have and colors outside. And then I have MP and M star P applied to K Z I will it will give me P of Z I bar which is the eigenvalue, and then the eigenvalue. That this is scalar, and it's not any scalar. It's by the interpolation condition is just Wi, because it just asks phi of Zi to be Wi. So it comes outside, it becomes Pi J Wi bar. And the multiplication operator at k is I is phi. I use the reproducing property again. W prime P and Z J with the reproducing property K Z I Z J. Again, phi of Zj is just Wj per the interpolation condition. And this is Pi J bar Wi bar Wj K I. And now when we compute the left hand side, the right hand side, we know that one is less than the other, which means that the difference is positive. So, you know, the right hand side minus the left hand side, and this is exactly equal to times J. I have Pi, Pj, which is the common factor. K, Zj, Zi, which is a common factor. And what it remains is 1 minus, since I bring the left hand side to the other side, W I bar W. So this is K that I. Which is the definition of saying that this matrix is positive. Okay, what I claim is that the conjugate of this matrix is positive, but it's the same thing, because saying that this quantity is positive for every Pij is the same, but taking the conjugate being positive. Okay. So this implies that 1 minus W I positive for every one given the complex number. Which is equivalent by definition of saying that this matrix is positive semi-definite. And it proves in great generality the necessity of the positivity of the big matrix. Which, as you saw, is just a reformulation of the fact that a certain operator is a contraction in the end. Okay, of course, So now I told you that the multipliers of the polynomial space are the zero set, which means, of course, that this condition cannot be always sufficient. Because, for example, for the polynomial space, you can find points which satisfy this positivity condition. But since there are no multipliers, no non-trivial multipliers, of course, you cannot solve any problem of interpolation by multipliers. So in particular for the polynomial space, this is not a sufficient condition. There is no sufficient condition that exists on multipliers. Which means that we cannot anymore argue by some Hilbert space method. And in fact, as I mentioned before, sufficiency of this condition is a property of the particular kernel that we choose. And we cannot do any better other than give a definition which says that if this sufficient condition, if this condition is also sufficient, then our kernel is special and we call it fixed kernel. So if H is the reproducing kernel, it's the positivity of the peak number. So intended for any choice of Zi and any choice of Wi and for any n number of points, the positivity of this matrix implies the existence of a multiplier in the unit ball of multipliers of which solve the interpolation problem. Then H, just emphasize the kernel here, it's said to have the peak problem. And that's pretty much the best I can do to give a definition. Okay, how rare are these spaces? How often they come across? There is a whole theory behind it. It's not covered. But let me say that. Okay, of course we have an example, right? The Hardy space, because we proved that for the Hardy space this condition is also sufficient. So the Hardy space is the primary example of a space with peak problem. And there are many others. Even classical space studied since the 70s or 60s. Let me mention a very. Miriam is not online, right?
No, she's not.
Now, okay, so for example, with Miriam and Nicola, we had this particularly elementary example of the space with the peak property. Just take the space of absolutely continuous functions in R such that with this norm. And maybe to make it say so this is also a space, so that's absolutely continuous function, so this derivative is defined almost everywhere. And you want this norm which comes from here for it to converge. This is the Hilbert space, and you can prove that it also has the peak property. So you see that it's some property that it's not only it's not strictly related to holomorphicity, let's say. You can have spaces of functions which are even defined on the real line, complex valued functions which have the peak property. So there are a lot of examples. That's
Sorry, Nico, what is AC?
absolutely continuous. you know, that is locally is the antiderivative of an L1 function. Yeah, but of
Loc-
course, the,
Locally is the antiderivative of what?
of an L1 function. Yeah.
Ah, okay. Mhm.
Yeah, just that one. I mean, of course, the primary examples of the hard space and other, but you have a lot of creatures out there. So yes, and then in the end, I wanted to. So it makes sense to consider properties of these fixed spaces. For example, I wanted to mention to you that the question of zero sets. So we saw that for the hard space, for AC infinity, zero sets are exactly. So we saw that there exists a function in AC infinity which varies on a sequence of points. And P is not identically the zero function if and only if we have this Blaschke condition. So again, the reproducing kernel Hilbert space theory can give us at least one direction of the two. Surprisingly, maybe there is sufficient direction in this case. So let's see that. So you can prove the following. You can prove, suppose that ace is the reproducing kernel Hilbert space with the peak property. So now we feel justified to include this peak property in the assumptions of the theorem. And suppose that you have some kind of, you could see it as a Blaschke condition for this abstract space. So suppose that 1 over k z I at z I invert this, so that I is a sequence that I choose. For some z I infinite sequence, then I can find the function. So I can, I would like to say that it is in the multiplier space. Actually, you can make it lie in the multiplier space, but just to simplify a bit the proof, I will just construct it in the Hilbert space itself. So there exists a function f in the Hilbert space. It is not the zero function, and it lies, it binds on this point. Yeah, so I said you can make it actually be a function in the multiplier space, but it requires a bit of more functional analysis, which I would like to avoid. The point is to highlight the idea. So the proof. So I will make an assumption which I will be able to remove later, maybe today, tomorrow. Assume that you have some point, distinguished point Z0, where the kernel is identically equal to 1. Okay. So if you are in the hard disk space with this kernel, if you put Z equals to 0, then the kernel is identically 1. And you can normalizing things, you can do it always, but assuming for the second, and then we can remove this assumption. Yes. And then, so what is the idea? Okay, here is my distinguished point, Z0. And I have a sequence of points, infinite, where I want to construct a function which vanishes on all points, but it's not identically 0. So it would be enough to make it not to vanish at one point, Z0. So the point is that I construct some multipliers which are 0 on Z I. No. So I construct a sequence of multipliers to be precise, I, such that they are 0 at Zi, and at Z0 they are as big as possible. And then I multiply all these phi together, and I hope this infinite product not to converge to 0 at this point Z0. So it's very reminiscent of the idea of Lasker products. Only that here we can carry it out in the abstract setting. So I want this phi to be a multiplier of, for some integral requirement of multiplier norm less than 1. Otherwise, you can state everything. I want it at Zi to be equal to 0, and I want it at phi at Z0 to be some delta I positive, which I want to fix it later to be as large as I can. Right? But this is a two-point interpolation problem, which, since I am in a big space, I know that it can be solved if and only if the corresponding matrix is positive. Okay, so a solution to this problem exists by definition of the big property if and only if the following matrix, so 1 minus, so let me call this W, so that will be W1 squared. So that I write the peak matrix. Where okay, Z1 is Zi in reality, because the points where I interpolate is Z0 and Zi. W1 is 0 because the value that I want to interpolate at the second point at Zi is 0. So this one is. And W0 is thus delta I. So the matrix is in fact 1 minus delta I, where K of Z is 0. Okay, so the idea is again, I have a 2-point interpolation problem, sending Z0 to delta I and sending Zi to 0, to say that for W0 and W1. And it's solvable by a multiplier of norm less than 1 if and only if this matrix is positive. This matrix is this matrix because W10 is W1 0. And furthermore, I assume the normalization that the Z0, this is identical in the function 1. So this is just 1, this is as well, this as well, and this is K of Z. Okay, I have a 2x2 matrix, which I want to be positive semi-determinant. This is equivalent to the first entry to be positive and then the determinant to be positive. So this is positive if and only if delta I is less than 1 and the determinant is positive, or in other words, this thing is positive. Or rewriting things if delta I is less or equal than 1 minus so that's the biggest value I can put on delta I, and that interpolation problem to still have a solution. In fact, I can be a bit generous and put I can define delta I to be 1 over 1. This is smaller than that. This is the number between 0 and 1. Okay. So now the peak property tells me that I have this multiplier. So there exists a multiplier Phi of norm 1 such that P of Z0 is delta I and P of Zi is 0. And as I said, the idea, as with Blaschke products, is to multiply all these things together.
We get Sky.
What is the FII mean? Yes, and I define phi capital N to be the partial product. Yeah. Thanks. So at Z0, this function is equal to the product of these things. And by calculation, we did it many times. This is the exponential. And we logarithms of 1 minus And we bound below the logarithm. Which here, again, I use this inequality that we use in France. But the point is that by assumption this thing converges, so this cannot be less than the exponential of the infinite sum, which is a strictly positive constant. Okay, so we know that if this thing converges somewhere, then at the point z0 it cannot be 0, so the limit function will be non-zero. And of course, at all other points, because one of these factor vanishes, it is equal to 0. And if you give me 3 minutes, I can show it also converges in the Hilbert space to something. So the point is that so we have to use the fact that the multiplier norm of phi are all bounded by 1. And when you, in general, maybe I forgot to mention, but if you take the multiplier norm of the product of two multipliers, this is the operator norm of the composition of the two multiplier operators from by the anyway, by this property of the operator norm, then this is less or equal than the product of the multiplier norm. So if I take a product of n things, then this is less or equal than the norm, the product of the norms. This is less or equal than 1. But the Hilbert space norm is bounded by the multiplier norm. So this is a sequence of vectors in the unit ball in the Hilbert space. And it had a weak star limit point. So there is a subsequence which converges weakly to some function phi in H. And of course, this limit function has to have these two properties, because weak convergence implies point-wise convergence by pairing to the kernel vectors. And so this function phi we constructed.
Maybe normalization of one blocks space.
Yeah, but
You get that in quality.
yeah. Sorry, I was.
Right.
So K, yes, we have we have this normalization that this vector belongs to the space. Okay. So the multiplier norm of P is the sup of all P and divided by F for F in the space 1, 0. In particular, since the constant function 1 is in the space, this is bigger than P times 1, which is P, divided by the norm of the function 1 in the space, which is 1 because the norm of K z 0 is just K z 0. So yes, this inequality, to get this inequality, you need the normal, you use again this normalization that we have. It seems I don't have time now. We can discuss about this tomorrow. So you can also deal with this thing with zero sequences in the abstract, in an abstract way. Again, it fails, the other direction fails. This condition is not necessary now for zero sets in abstract representation. It's only sufficient.